So a very good afternoon to everyone. Welcome to today's live lecture session on Introduction to Geosynthetic Applications. This is the second lecture of this short course. So in the previous session, we learned what are the types of geosynthetics that are available, what are the different types of polymers that are used to manufacture those geosynthetics, what are the different properties, physical, mechanical, hydraulic properties, and different ASTM or ISO standards that are available that deal with the testing of different types of geosynthetics, different types of properties of different types of geosynthetics. All those we saw actually yesterday, right? So in today's session, we are going to today's class, we are going to see the mechanism of reinforced earth. Right, we are going to see the mechanism of reinforced earth, the reinforced soil, and yeah. So let us slowly start the session for today. And if you have any doubt, please feel free to interrupt and ask me anytime. You can also write your queries in the chat box, or you can even email to me afterwards, after the class is over. The recordings of the classes are also being shared with you. So if you want, you can watch the recordings anytime at your own convenience. And apart from that, I'm also sharing the PDFs of these presentations with you. Okay, I hope you are able to follow through the lectures, and I hope that you get to learn something from this short course. So let us begin. So a short acknowledgement before I start the lecture. So what is triaxial compression test? So triaxial test we all have studied in our soil mechanics or geotechnical engineering courses. How the triaxial compression test is done and what triaxial test is. So triaxial test is basically there are three types of tests: unconsolidated, undrained, consolidated, undrained, and consolidated drained. So three types of tests are there. So we are not going to discuss them in detail because we already have studied in our basic soil mechanics or basic geotechnical engineering courses. So we are not going to repeat that again. We are just going to brush up the whatever knowledge we have. Right? So triaxial compression test, we have three types, right? We have we have CU, yeah, CD test, right? Now, what is the H by D ratio of the sample in a triaxial test? So triaxial, we know that we are having a cylindrical soil sample, right? We are having a cylindrical soil sample. That we have a cylindrical soil sample. So what is the H by D ratio that is maintained in the soil sample? That is generally around 2. Right? Now the triaxial sample, in a triaxial sample, so we have the sample. So what we do initially, we apply some confining stress throughout, which is nothing but our minor principal stress. And after that, we apply the deviatoric stress. Right, we apply the deviatoric stress. So what is my major principal stress? Is nothing but deviatoric stress plus the minor principal stress. Right? So deviatoric stress is nothing but major principal stress minus the minor principal stress. Okay. Now, what are P and Q? So P and Q, P is the stress and Q is the deviatoric stress. Okay. Now, normal stress on any plane. So we are doing a triangular test. We have any plane that is inclined at angle say theta with the horizontal, that is any plane angle inclined at angle theta. What is the normal stress on any plane? It is nothing but sigma m equal to similarly the shear stress on any plane. And what is the inclination of the failure plane? The inclination of the critical or the failure plane is 40 by 50 plus I by 2. And phi is the angle of internal friction. Now, what is the basic equation that we know? Basic equation is that fail F means at failure. So I am not deriving all those things, because you already know this from your soil mechanics courses. So you won't spend much time. You can write this as 10 square multiplied plus 5 by 2, 3 plus 2 10. Okay. So 10 square 45 plus 5 by 2 is Kp, right? Possible to Kp. Kp is what? The passive earth pressure coefficient. So you can also write it as, okay. Now let us see this triaxial test on reinforced sand. Okay, reinforced dry sand. So first, so what we are doing here, we have a cylindrical soil sample, right? So what we are doing, we are reinforcing it with some material. Okay, so this is our soil sample. Our soil sample is reinforced with some kind of geosynthetic, maybe geogrid or geotextile, whatever. Okay, it is reinforced with some kind of material. Now, first, what we do, we test an unreinforced soil sample, just a normal unreinforced soil sample. We test it, we get this particular curve. Next, we put only one layer of reinforcement. Then we get this. Then we make 3 layers of reinforcement. Then we get this, and then again we increase the number of reinforcement to 5 layers. Then we get this. So, what are our observations from these curves? Higher strength and stiffness for reinforced soil. So you can see as the soil is reinforced, the stiffness. Okay, this initial stiffness is increasing, right? It is soil is becoming more stiff, right? So more reinforcement gives higher strength and stiffness. Okay, so as we increase the reinforcement, the soil is becoming more and more stiff, and we are getting higher strength. Okay, the you can see the peak value of the strength is increasing, right? So initially unreinforced it is this, then as we are increasing the number of reinforcement, the peak is increasing, right? All responses are similar at low strain level. So, but at very initial low strain level, say in this region, the responses are almost same, right? The behavior is almost same because because as the strain increases, there has to be mobilization of the forces in the reinforcement. If the strain is low, at that time the reinforcement, the forces in these reinforcements are not yet mobilized. So hence all these curves behave as the same initial portion. But as the strain increases, the strength of the reinforcement get mobilized. So as this mobilization happens, you can see that there is a differentiation between these stress strain plots. Okay. Now this was for a confining pressure of 25 kPa. Now if we increase the confining pressure, obviously it is going to fail at a higher load. Okay, before at 5 layers, it failed at around 450. Now at 5 layers, it is failing at around 1100 kPa gravitational stress. So as the confining pressure will increase, obviously it is going to fail at a higher load, right? But At higher confining pressure, we are seeing that the initial portion remains the same for both unreinforced and reinforced cases for a longer strain range. Okay, longer strain range. But here it was initially only in this part. But here up to this much strain, the initial portion is almost same. Initial stiffness is almost same up to a larger level, larger stress level. This is because when the confining stress is higher, we need larger strains to develop for the reinforcement forces to get mobilized properly. Okay, we need a larger strain to develop for the reinforcement forces to get mobilized. Okay, so understood, right? Now, now these are the QP plots for unreinforced and reinforced cases. So what do we do? How do you get the Q? You do some test, right? You do triaxial test, and then from there triaxial test, and from there you get the Q and P value, and from there you can get the fiber. So one more option is that you plot the more circles. You can plot the more circles and draw the tangent like this, and then you can find the phi value, right? Phi value. But one more option we have with us is that we plot the QP value. So plotting the QP plots are easier than drawing circles, right? Plotting QP plots are easier than plotting circles. So what we do? We plot the QP plot. So you already know what QP is, right? So in the x-axis, we have the our P, and here we have the Q, right? So we will get, say we get some graph like this. So this slope is beta and this intercept is A. From A and beta, how can we find our C and phi? How can we find our C and phi? So phi is what? Sine inverse tan beta, and C is A by cos phi. Okay, we get the phi and the friction angle and the cohesion of the soil from the PQ plots. Similarly, for our case also, we plot the PQ plots for the unreinforced and the reinforced case. So we are seeing that for the unreinforced case, the friction angle is 41.2 degree that we are getting. But for the reinforced soil, we are getting a friction angle of 49.1 degree. So for the same soil, unreinforced, we are getting 41.2 degree. And for the reinforced soil, we are getting 49.1 degree. So the as we reinforce the soil, the friction angle increases for the whole soil increases. Now, this increase, so we already saw that as we reinforce the soil, with some kind of reinforcement, maybe geotextile, geogrid, whatever, the strength of the soil is increasing. Right, the strength of the soil is increasing as we reinforce the soil. As we reinforce the soil, the the strength of the soil is increasing. The strength of the soil is increasing as we are reinforcing the soil. So how can we explain this increase in strength? So this increase in strength can be explained in two ways, either as increase in friction angle or as increase in development of an apparent cohesion. Okay, you can explain this in a two-way fashion. Either you can say that the friction angle is increasing, or you can say that apparent cohesion is developed, due to which the strength of the soil is increasing. So what is this increase in friction angle? So this red plot here is the Mohr circle for unreinforced case. So unreinforced case, phi is that for the unreinforced case. Now say what is happening. Say our soil strength is increasing. That means what? When you are putting some reinforcement, we can think it of in that way that the soil will say the soil was failing at a load of 100 kPa before. 100 kPa at 20 kPa confining stress, the soil was for unreinforced soil, and unreinforced soil at 50 kPa confining stress sigma 3, it is failing at a major principal stress of sigma say 100 kPa. A 50 kPa sigma 3, it is failing at sigma 1 at 100. Now, if we reinforce the soil, what will happen? We can think it of in that way that for even lower sigma 3, for even lower sigma 3, say now reinforced soil. So before unreinforced soil, sigma 3 at confining pressure of 50 kPa, it was failing at 100 kPa. Confining 50, it was failing at 100. Now reinforced, say what will happen at lower confining, say 25 kPa confining, at 25 kPa confining, it is failing at the same same sigma 1, 100. So before, for unreinforced, we need a sigma 3 of 50 kPa for that soil to fail at 100. But for reinforced case, we will need only a sigma 3 of 25 for our soil to fail at 100. Okay, so that we can explain it in that way. So unreinforced case, you say it is failing at the same sigma 1, but now a lower sigma 3. Then if we draw this, we will get the increased friction angle. Okay, that this is one of the explanations that we can give. Now, other explanation that we can give is the concept of apparent cohesion due to reinforcement. So now say this is the circle. So this is the circle. Sorry. This is the circle for unreinforced case, right? The blue circle is for unreinforced. Blue circle is for unreinforced. Okay, blue circle is for unreinforced. Now, say we are having the same confining pressure. Okay, so unreinforced, it was failing at this sigma 1. Now, so this is for the unreinforced. Now, if we reinforce the soil at the same sigma 3, that's the opposite to the previous one. So unreinforced 50 kPa, it is failing at 100. Now reinforced 50 kPa, it will fail at say 200. 50 kPa same sigma 3, but it will now fail at a higher. So now if we draw this here, so we get a cohesion, right? So this apparent cohesion explains the increase in strength. Okay, increase in strength. Okay, and what I was saying is that, yeah, right, understood, right? Okay, now things that matter the most, things that matter, these are the things that are important in when we are discussing about reinforced soil. These are the important parameters: the spacing of the reinforcement, the spacing, the gap, the density of this that which you are placing the reinforcement. It is the spacing of the reinforcement, the strength and stiffness of the reinforcement. Obviously this is going to be one of the most important things, and the interaction between the soil and the reinforcement, that is the friction angle between the soil and the reinforcement. So these three are the important things that are important. These are three important parameters that are important in the reinforcement, right? Right. Now there are two main major failure modes when you are discussing about reinforcement. One is the pull out failure and other is the rupture failure. One is the pull out and other is the rupture. Okay. So let us see what these are. Okay. Pull out and rupture. Now say this is a soil. Okay, this is a soil block, and in the soil block we are having a reinforcement that is embedded up to embedment length L. Okay, this is embedded, and we are also applying some normal pressure. Okay, you are applying some normal pressure sigma B. Okay, we are applying some normal pressure. This was normal pressure we are applying at the soil. And we have a reinforcement that is closed. Now, this reinforcement can fail in two types, pull up or rupture. Now, let us see what these are. Let the tensile strength of reinforcement be T. Okay. And let the width of the reinforcement be P. So Tu is the tensile strength of the ultimate tensile strength of the reinforcement, and P is the width. So that is width means the out of plane, out of the plane of the computer screen, whatever the direction. In that direction, what is the length of the reinforcement? That is the width. So that is why width. It is B. I am using. Now here resistance developed along the reinforcement RP. We are calling it as RP. What is this? The shear resistance means this is the shear resistance that is developing at the interface. Okay, interface between the reinforcement and the soil is 2 times. Why 2? Because we have two surfaces. This is one surface, upper surface and bottom surface. That's why we are having term 2. 2 times sigma V times L times beta B times 10 delta. Okay, there is nothing but the normal stress times the area in which the stress is acting times tan delta. What is delta? Delta is the interface friction angle between the soil and the reinforcement. Okay, so this is delta. Now, if Rp is greater than the ultimate tensile strength, then what will happen? Then pull out failure occurs. Now, if Tu is great, and if Rp is less than Tu, then rupture failure occurs. So there is chances. So if the pull out this resistance is greater than the tensile strength. Okay, then what will happen? Pull out failure will occur, and if the uh, just a second. So see, pull out when. So let us not write this first. Let us understand before writing. So when will pull out occur? Pull out will occur when this resistance is less, but this tensile strength is high. So it will just pull out. This resistance that is holding the resistance that is holding the reinforcement is placed, it is less. So when some this will come, it will just pull out. So when pull out failures pull out failure occurs when my resistance is sorry when my Tu is greater than the Rp. That time what will happen? My pull out failure will occur, right? And when rupture failure will occur, when U is less than Rp, right? That means much. My resistance is higher than the tensile strength. At that time what will happen? Rupture failure will occur. And if my TU is greater than RP, then the full earth failure will occur. Okay, just give me 1 second. Huh? Yeah. So understood, right? So when TU is greater than the resistance, so this is the resistance of the soil and this is my reinforcement. So there is a force coming on the reinforcement. So if the resistance is, if the tensile strength is higher than the reinforcement, then what there are chances that the reinforcement must might come out from the soil. Okay, my reinforcement might come out from the soil. Okay, okay, what will happen? There are chances that the reinforcement might come out of the soil. But if my tensile strength is less than the whatever the force that is there, that the shear resistance, then what might this reinforcement must break away. Reinforcement might break away, so that is the rupture. Okay. But so now what we are going to do, we are going to do the equilibrium analysis of a soil bed. So say this is a soil. Okay, this is a soil. Soil, reinforced soil. Okay, this is a reinforced soil. BC is any plane. We have the major principal stress, minor principal stress acting, and the soil is reinforced. Now, say we are getting any wedge ABC. In ABC again, this sigma 1 is acting, sigma 3 is acting. Okay, and this theta is the angle that this wedge makes with the vertical. Okay, and so at this plane, BC plane, where we will be having a normal stress that will act, we will be having a shear stress that will come, and one more term that we are seeing here is the summation of T. The summation of T, the summation of T is nothing but the tensile or the resistance or the whatever tensile uh, forces that are generated on the reinforcement. Okay, that is our summation of summation of T. So in this plane, this is the normal stress that is in, this is the shear stress that is acting, and summation T. T is nothing but a total reinforcement force that develops on the plane PC. Okay, so we will write it. Okay. In equilibrium under action of start by the plane. Right? So total reinforcement force is sigma T developed in all layers cut by the plane PC. Okay. Let the length DC be equal to B square. So my AC is what? Okay. Now if we take the summation of all the vertical forces equal to 0, get summation of horizontal forces equal to 0 plus plus sigma is tau is sigma and 10 phi not theta. Because of soil to soil interaction on BC. Right. Tau is sigma and 10 phi because here in this part there is soil to soil interaction, right? There is no interaction between uh, the reinforcement and the soil. Else we would have used delta. Substituting tau in equations 1 and 2, we get cos theta is 4. Okay. Now from question 3, okay. Now putting this in so finally from here what we will get is we will get Okay. So earlier what was the number? Is 5, 6. Okay. So what is T? What is summation T? Whether it is the sum of the total reinforcement forces, okay, cut by that wedge, right? So if SV is the vertical spacing, then number of reinforcement layers cut by the wedge is E cos theta by SV. Okay, SV is the spacing, then the number of reinforcement layers cut by the wedge is B cos theta by SV. If U is the tensile strength, a single reinforcement layer, then T is so this is called the rupture capacity. If pull out is the failure mode, the net tensile force generated at the verge of failure is mu br b cos theta by sv, which is this. The mu is friction factor, nothing but tan delta. Okay. Now there are two cases. Okay. If there is rupture failure and if there is what? If there is pull out failure. Okay. So we got two here options here. What summation T? The summation T if rupture is the mode of failure, then summation T will be this, and if pull out is the uh, failure, then this will be the thing. This will be the summation T. Br is the width of the reinforcement. Okay. Br is the width of the reinforcement. Now case one. Rupture failure. Into 10, I'm writing it here. Huh? So sigma 1 will come out as sigma 3 plus by 9. Excuse me. Okay. So yeah, now now the question is, what is the limiting value of sigma 1 at which failure happens as theta is the arbitrary value. Okay, so theta is our arbitrary variable. So we're going to find out the limiting value of sigma 1. For that, what you can do? You can do this thing. Okay, you can differentiate and make it to 0 so that we get the maxima or minima, right? So 0 from here we will see theta comes out as 2 minus 2. So which is a familiar value that we get from Rankine theory, right? Now substituting this this in the equation will get, therefore sigma 1 is two. Therefore sigma 1 r is sigma 3 plus tu by sv into 18. Yes, 10. Okay. Now for unreinforced soil, there is no contribution of the reinforcement. At that case, for unreinforced soil, what is my sigma 1? Is sigma 3 into Kp, right? C is 0, where considering C is 0. So this is by sigma 3. And for reinforced, and for reinforced case, what did we get? Plus 2ic root over Kp. Okay. So from here you can write sigma 3 plus, this is for the unreinforced case. For reinforced case, we have this one. Again, we know that for the reinforced case, we are getting this equation here. So if you write, you can write that also. Escaping. So, so if you equate these two, we get equating the equations. C is our apparent cohesion. Is nothing but u by twice sp. Over. Yes. So what we saw when case, this was case 1, right? Rupture failure. So when rupture governs the rupture failure governs the mode of failure. When rupture governs the mode of failure, at that time, apparent cohesion describes the increase in strength due to reinforcement. So initially we saw that there are two types of explanations that can explain the increase in strength. One is the increase in friction angle, other is the development of apparent cohesion. So when rupture is the mode of failure, at that time apparent cohesion is the defines the increase in strength. Okay. Next is the pull out failure. Okay. Just give me one second. I will just add some slides and get back. Okay. So now we will see the next case. What if our pull out is the failure? There is a sliding failure. If there is not rupture, there is a sliding failure. Okay. Case to pull out failure. So in this case, ah, so in this case, substituting for equation 6, get sigma 1 as okay. So again for finding the limiting value, one, two, 0. Again you will get theta s. Okay, again we will get the same thing. Therefore, that is 10 square. Okay, so this Kp bar is obviously less than greater than Kp, which implies phi r is greater than phi. Okay, Okay, so Kp, why, how Kp bar is greater than Kp? So Kp bar is what? Kp times 1 minus some value, right? 1 minus some value. So this value is obviously be positive. So 1 minus some value. So the term in the denominator is going to be less than 1. It's going to be between 0 and 1. So Kp divided by some term which is between 0 and 1, some fraction between 0 and 1. If we do, then we will get Kp bar as some uh some in the some so a number times Kp, right? So Kp bar is always obviously greater than Kp. So we get, therefore my reinforced friction angle will be greater than friction angle. So we can say that friction angle of the reinforced sand will be more than that of the unreinforced sand. So and the when the failure is by pull out. So we got two things. When the failure is by rupture, at that time apparent cohesion explains. Write it. What is failure by rupture? Then the increase in strength of the soil is given by the apparent cohesion. And when failure by pull out, then increase in friction angle explain the increase in strength. Okay, so these are the two fundamental things that we have. Now, one more important thing you should remember: at low confining pressure, pull out failure will happen. There are chances of pull out failure to happen. And at high confining pressure, rupture will happen. Now, what is the limiting value of confining pressure? So, if the confining pressure is less than this term, then pull out failure will happen. And if the confining pressure is more than this particular value, then rupture failure will happen. Okay, so this you should remember. Okay. Okay, so what do we have? Okay, so you see this question. I'll give you a minute. Read this question and try to solve it by yourself. I will give you 1 2 minutes. Just try to do it by yourself. Okay, just try to read the question and try to understand the question and try to do it. Try to do it. Try to solve this problem. So did you were you able to solve it or not? You're able to understand the question? It's very simple, right? Very simple and direct. So what is asked? Given the ultimate answer, TU is 30 kilonewton per meter. The friction angle is of the soil is 30 degree. The spacing of the reinforcement, the vertical spacing of the reinforcement is 0.5 meter. The width of the reinforcement is 0.05 meter. The friction coefficient is 0.6. If the confining pressure acting is 200 kPa, which type of failure will happen? Accordingly, find the apparent cohesion on increased friction. So first we need to identify which type of friction, which type of failure is going to happen. On the basis of that, we are going to see whether apparent cohesion governs or increased friction angle governs the that mode of failure. And accordingly, we'll find that out. Okay, so let us do very simple. You should have done it. Actually, it's everything just now whatever we discussed. That's all. That's the thing. So emitting confining stress pressure limit is what? Tu 1 minus twice PR mu SV dB by twice PR mu Kp. So we put the values 30 1 minus 2 into 0.05 and 0.6 and 0.53 by 2 into 0.05 times 0.6 times 3. So how Kp you are getting 3? Kp is what? 1 plus sine pi by 1 minus sine pi. Put phi is equal to 30 degree and this is 3. So this is coming out as 106.7 kPa. Okay. Now as our acting sigma 3 is 200 kPa is greater than this limiting value, and tell me which kind of failure will happen, pull out or rupture. Pull out or rupture, it is greater than the limiting. So rupture will govern, right? So we'll have rupture. Okay, now see if rupture is the mode of failure, then apparent cohesion governs. So apparent cohesion you have to find out accordingly. So what is the apparent cohesion? PU over KP, right? So we just found that out a while back. PU by twice root over KP. Okay. To 52. Okay. Similarly, try to solve this problem. It's very similar. Try to solve this problem. Just wait for 2 minutes for you to think and solve, then I will solve for you. It's very similar problem. Just try to solve it. Same, right? Same. Just similarly, you have to find out the limiting value first. I hope all of you are able to follow these things, huh? Now my sigma 3 is 50 kPa. So sigma 3 is less than my sigma 3 limit. So pull out failure will occur. Sorry, pull out failure occurs. That means what? Pull out failure occurs. That means what? My increased friction angle will be the explanation. Right. So how to find that? We find Kp bar. Here. So you put 4.69. So it will sign by R as 0.6485 by R as 40.43 degrees. This is the increase. So initially say 30 degrees, but now due to the reinforcement, my friction angle has increased to 40.43 degrees. Okay. Now let us just see this a bit. Just a second now. Now, this approach, the Hosmer approach is nothing but it's another just point of view of looking at the increasing strength due to reinforcement. Whatever we have studied is the same thing. So what it's written here, let us see. Due to the reinforcement, the reinforced soil develops higher strength when tested at the same confining pressure. So as I said, as we discussed in the beginning, so at the same confining stress, it will have a higher strength. Okay, due to the reinforcement. We also think that we need lesser external pressure to develop the same failure. Same whatever I discussed with. I discussed these both things with you. Okay, today in the beginning of the class, I discussed these things, right? So these two. So this is the same thing. So this is nothing but the Haussmann. Okay. So sigma 3 is Ka times sigma 1, sigma sine pi is this, and sine pi r can be written by this. So if this is for the unreinforced, this is the unreinforced, then for reinforced, you can assume it that it is attaining the same failure at a lower confining stress sigma 3 r, a lower confining stress sigma 3 r, and the difference is sigma r. This difference is sigma r. Okay. Now, so I have written it like this, written the equation like this. Now again, I can rearrange it to like this, right? Now, sigma is the additional confined pressure induced in the soil by the reinforcement layers. Okay, this is the additional that is actually given by the, not supplied by us, but it is actually given by the reinforcement. Yes, that is my sigma r. F is a factor, it is given as sigma r by sigma 1. Okay. Similarly, so sine phi r can be written like this. written like this, right? So here you can see obviously denominator is going to be less than 1 higher, so sigma sine phi r will be actually higher than sine phi. Okay. Similarly, it can be explained by this approach, that is our what I said, the previous approach where I explained the apparent question stuff. Similarly, we'll get this. Okay, it's the same thing, just we are explaining it in different. Now, what is sigma? Sigma, I said, this is the strength. It is sigma is directly related to the strength of the reinforcement, the vertical spacing, and the interaction and other factors. So sigma r is, we say sigma r is the confinement given by the confinement induced by the reinforcement. Sigma is the confinement induced by the reinforcement. This sigma is directly related to the strength of the reinforcement, particle spacing of the reinforcement, and interaction between the reinforcement and the soil and other factors. So sigma is reinforcement per unit width times eta by SP. So TU times eta by SP. Eta is the efficiency factor to account for unequal distribution. Okay. Now we, up to this much, whatever we discussed, up to this much, whatever we discussed was was what? It was related to the mechanism of reinforced earth. So reinforced soil, mechanism of reinforced earth. Now we will be discussing about retaining walls, because slowly we are going to the design of reinforced earth walls, right? Reinforced soil walls. We're moving towards that. We are on the verge of that. Before we go, before we go to that, let us just see a bit why do we need retaining walls and what are the different types of it. Okay, let us just see that a bit, because we are slowly moving towards that. It's important for us to know, because we are ultimately what reinforced earth walls are also type of state where just designing it the structure in such a way the soil can stand on its own, that the soil can stand on its own. Else what? Else you have to put retaining walls, right? So that's why we are just proceeding to that point. We will just discuss about the retaining walls. That's so. Why do we need retaining walls? Why do we need retaining walls? Is it, so why do we need retaining? So we know the soil is very good in compression, right? Soil is very good in compression, but soil has very limited tensile strength and shear strength. Right, soil is very good in compression, very high compressive strength, but it is very low shear strength or tensile strength. Right, that's why we want to support the soil. In some cases, we need retaining wall. So why do we need retaining wall? To support the soil fertility. Why? Because soil is weak in tension and shear. Now, say if we what we do, we drop some soil from a height, we free let the soil drop, free fall, so soil go through, have some free fall and some attain a shape. So it will attain a heap of soil like this sand, say, attain. So it will, this will my five angle, this is nothing but friction angle will over the angle of repose of the soil, right? So now say we want the soil to stand at a steeper configuration. So we have to want the soil to stand straight. So for that, what we have to do? For that, what we have to do? We need to put some retaining wall here. We need to put some retaining wall here, right? Now, what are the different types of retaining walls? So now tell me, you already know these things, right? So what are the different types of retaining walls? So first one that we see, that is nothing but the gravity retaining wall, right? Gravity retaining wall. And these are what? These are RCC cantilever retaining walls. You can see this is the stem, right? This is the stem. This is the toe. This is the toe. This is the heel. This is the shear key, right? This is the active earth pressure that is acting. Okay. all those things. Okay. So what is the benefit of this hierarchy? So when so as soil here will give some passive resistance to the retaining wall. So that's the action of the hierarchy. All right, the action of the hierarchy. Okay. So this side will have active, here we will have passive resistance, the soil, all those stuff things we will have. Okay. And now these are board types of retaining wall. This is called a counterfort retaining wall. So we have some counterfort placed here. Okay, counterforts placed here. There are counterfort retaining walls. They're called buttressed. So if the counterforts are placed on the other side, it becomes buttressed retaining wall. These are sheet pile structure. Sheet piles. These are sheet piles. So say uh you want to we have soil here outside. Okay, we want to construct something in between. So what we do, we drill, we hammer sheet piles, we make this wall-like structure with an interlocking piles known as sheet piles. So these are small like the sheets which interlock with each other. Okay, so we drive them with a hammer, with the help of a hammer into the soil, and it forms a wall-like structure. Okay, so inside we can do any construction or something. Maybe want to build, we can do that. And these sheet pile structures actually buttressed also. Here, see, you can see these beam members are there. These buttressing members are there. These members are actually buttressing also. Somewhat. Okay. We want to sheet files. I can show you here. Files. Okay, so these are sheet piles. These are used in many offshore like shoreline protection, many stuff. While if you want to when during the construction of piers, you want to make a coffer dam and all those things. So this is a copper dam. So there are many uses of these sheet piles because they are you just need to carry them and just to drill them. They're easy to construct, easy to build the structures. So these are quite helpful to us, especially in marine conditions. Okay. Then we have this anchored sheet pile. So the sheet pile is a sheet pile is anchored at the back. Okay. We drill it and we anchor it into the soil. They're anchored sheet piles. Okay, so these are buttressed again, buttressed sheet piles, buttressed sheet piles. These are struts that are there. We have buttressed. Okay, these are generally top down or bottom up approach. These are built. So it's I think top down only. We keep on pushing it again and we keep on excavating the soil and keep on pushing the sheet pile pot into the soil again and again. Okay, so then we have the reinforced. soil wall. So reinforced soil wall that we will be discussing more in this course. So reinforced soil wall, we have a soil, we have a soil backfill which is reinforced with these reinforcements. Okay, so this is the reinforced soil part, reinforced part. This is the retained soil. This is the reinforced soil because reinforcement are there in this what we call it reinforced soil. This is the retained soil, just the normal backfill soil. Retained soil, there is no reinforcement, we call it retained soil. This is the total backfill. This is the this combined everything is known as the backfill soil. Bottom we have the concrete foundation. Okay, these blocks that we saw some images in the first class, right? First class, yesterday's class, where we had some blocks and then we had the geogrid placed between the blocks. So these blocks are modular blocks. They're called modular blocks. These blocks are placed. Okay, so these reinforced earth walls are also types of retaining wall, right? Then these are some more, you can see these are some more nailing. Okay, these are nailed structure. Nailing is done. So what we do, we have a slope, we put nails in it, and with the when we do when and then we lighten the nail here, we put these anchors here, reinforced plates here. Then we can put these steel meshes, and our the steel meshes we can do some shotcreting. That is, you can spray concrete. So this makes our slope stable. So you can see this is my slide zone, but what you are doing, an anchoring the slide zone behind at the back at this one. We are anchoring this with the help of this nail. So whenever this soil will try to uh, come out, push down, this there will be some passive resistance that will develop in this nail. It will try to pull it back into its position. Okay. Okay, so this is the normal mechanism. Right. So this is that only, and nothing more. Then we have types of retaining wall. We have these precast concrete panels that are based, and we can tie them with anchors behind in the soil. Okay, so this is the front face, this is the plan view, these are the reinforcing elements that are anchored. All this. So now let us see this video of soil nailing that I was saying. Huh? Let us so initially we'll see that these kids are doing some experimentation. Small experiments in a box. They will make a slope, and then I will put some load with some books over the slope. And say it is failing. Then they will nail the slope with the help of some long wooden toothpicks. And then they will look into the experiment. They will see that the soil is not failing. Okay.
Soil is a soil reinforcement technique used for protection and stabilization of natural or excavated slopes. The technique improves the overall stability of in-situ slopes and restrains the slopes from failure. The technique also has advantage of strengthening the slope without accessing earthwork to provide construction access and working space either for permanent or temporary purposes. First thing first, the position of soil nails in a grid pattern are to be set out. So we have to ensure that the horizontal and vertical spacings are correct, and the inclinations and the angle of inclinations are also checked during the survey. Then we mark the position with pegs. Typically, the spacing of horizontal and vertical of the soil nails are 1000 to 1500 mm, while the angle of inclinations are 15 to 35 degrees. Then the drilling machine will be mobilized to the soil nail position. The drilling rod is then positioned and adjusted to the specific angle of inclination, which is at mentioned 15 degree. Then the operation of drilling will be started, and at the same time the drill soil will be flushed out by air.
So where you can actually see the process of this drilling, okay, with the help of
Here we can see that the air
yeah,
is flushing out the soil during the
see
operation.
this.
And this is how the machine, which is called the leader, have multiple pieces of extension that is used to extend the drilling rod manually. The video shows when it's done drilling, the workers are pulling the extension out one by one manually. Then, the steel reinforcement, which has a size of typically T20 to T32, has a length of 12 meter, will be inserted into the drill hole.
Reinforcement is being inserted. Okay, initially you drill the hole, you do air flushing. Okay, then you take out your drilling machine, drilling rod, and then you insert the
Then, the
reinforcement.
grout will be pumped into the drill
Right.
hole from the
After
bottom of
inserting
the
the
drill hole.
reinforcement, you
This is
pump
also
the
to
cement
ensure
grout.
that the soil at the toe level of the drill hole will be flushed out along with the grout to ensure the soundness and quality of the grout used in constructing the soil nail. The installation process of other soil nail at other positions will be repeated until the entire slope is completed. Then a gunite wall will be sprayed as per required in the construction drawing. Upon completing the gunite work, base plate will need to
So,
be installed and
so
locked on.
what you have to do? What you have to do? First, you have to drill the hole, then insert the reinforcement, then you have to pump the concrete in. After pumping the concrete, what you do? You make the granite surface. This is ganiting means you spray concrete. You spray concrete, which is also known as shotcreting. You spray concrete on that surface with the help of a gun. And after this surface is ganiting work is done, you put this base plate.
And sand mix to construct the soil nail cap, which will look something like the second picture, in which I will show in a second.
This is a soil nail cap that is made.
Now let's move
You
on
can
to
also use
modeling and
plates.
analysis.
Okay.
The model shows a slope that is without reinforcement.
Then they have
According
done
to the
some
slope stability factor of safety
this modeling in
for
this
the most critical
software
slip surface is
software
1.618.
called GeoStudio. This they have software called GeoStudio. They have done some modeling. If you want, I can play it also. You can see it is actually informative. After that, they will show the after this part. They will show their small experimentation that they have done.
Now let's move on to modeling and analysis. The model shows a slope that is without reinforcement. According to the slope stability analysis software, the factor of safety of the critical slip surface is 0.606, which is actually lower than 1, which means it will be very likely to slip off. After adding soil reinforcement to the slope, the factor of safety for the most critical slip surface is 1.618. This shows that the slip surface will be.
So this is a limit equilibrium software. Okay, so they are doing limit equilibrium analysis. The Swedish circle method and all those are Morgenstein's price and all those method analysis. They are doing that. Okay, slip circle method or this Morgenstein price method, whatever. Limit equilibrium analysis they are doing here. Okay, with the help of this GeoStudio. The GeoStudio is basically limit equilibrium software.
Unlikely to slip off, the factor of safety is also satisfactory according to the design code. From the local practice, the soil nail diameter are typically 100 to 150 mm, where the steel reinforcement ranges from T20 to T32. The spacing of the soil nails are typically 1000 to 1500 mm center to center with a typical inclination of 15 to 35 degrees. We have built a slope that is similar to what a real life slope would look like using soil, and then we place some weight on top of the soil until it collapses. In a few seconds, we can see from the side until a certain weight was added, which is about 26 kg according to our estimation and calculation based on the amount of paper and its unit weight, the slope became unstable and started crumbling down.
You can say the slope has failed. Okay, it could not bear anymore. Okay, now they are nailing the slope with the help of this wooden toothpicks.
Apparently, the slope hasn't even moved a little bit even after the same amount of weight is placed on top. Therefore, we try to put more weight on top and see how much weight it can sustain before it fails. Unfortunately, before the slope collapsed, our piles of paper which were not evenly placed on top has caused the paper tower to fall. However, from the side view, we can see that even when the piles of paper and report has fallen, the slope was sturdy and does not even move an inch.
Okay, so the load failed, but
Alright, I hope you
uh,
find this video helpful for you
paper
to understand soil nail.
the slope did not fail. Okay, so this was a short video, good, nice video, informative video about the soil nailing. Huh? Now let us see about reinforced soil walls. Okay, so reinforced soil walls can be many types. You can place two with geosynthetics. Geosynthetics such as geotextile. You can reinforce the soil with geogrid. We can use uniaxial, biaxial, both you can use, or we can use steel plates also. You can use to reinforce the soil. So many things are there. Or strips. You can use strips, or um, even you can use even geosynthetic strips you can use, or steel strips you can use to reinforce the soil. So there are many possibilities. So here you can see one full height panel wall is shown. So this is one configuration where the panel that you are there, that is there at the front, is one whole rigid structure. Okay, and then we are attaching here this reinforcement in many places. Then we can have segmented walls where these are not instead of being a total full structure, there are segments. Okay, segments of this modular blocks, segments of the wall panels. Then we can either also we can have these modular blocks that we already discussed. So we can have this block kind of thing. We place one above another, one above another. When we place the reinforcement like this here, that we can have. Also, we can have geotextile wraparound retaining wall. So this is one layer you wrap around like this. You again fill it this, place this one more layer like this is called wraparound. So this is called wraparound. Okay, this is called wraparound wall. So we will see the design of this. Okay, we will solve some problems in the next class. We will be dealing with the geotextile wraparound retaining wall. So a very interesting, very nice problem. We will solve tomorrow in tomorrow's class. Now these are the basic components of a reinforced soil wall. Okay, these are the basic components of a reinforced soil wall. So what do we have? We have first we have our foundation soil is there. Obviously, we have the foundation soil. Then we have this called leveling pad. This is called a leveling pad. Then we have the backfill soil. Okay, this is the retained soil. Then we have the reinforced soil. We have the reinforcement. Then we have the facing panel. Okay, so these are the basic constituents of the reinforced soil retaining wall structure. So thin flexible facing panels about 180 mm thick are used. Leveling pad is usually 150 mm thick and 300 to 400 mm wide. So this leveling pad is just a concrete, we are doing a concrete pad we are making so that we get a even level surface to place the blocks. Okay, the facing panels. Okay, we get a even area to place the facing panels. Then we have so backfill soil is generally selected as non-plastic granular soil, granular fill, and we use horizontal reinforcement here. So these are the basic constituents of a reinforced soil. Okay, so try to remember this. So leveling pad, facing panel, reinforcement layers, reinforced soil, backfill, and foundation soil. So now, next we are also going to see a video where this whole process of construction of a reinforced soil wall will be shown to you. All right. Now, Henry Vidal. Henry Vidal was a French engineer and architect. He was the original, he was the main person behind this reinforced soil wall design. Okay, he was the main father of this reinforced earth wall. So, so initially he showed that we can use reinforced earth, we can reinforce the earth with the help of steel strips, okay, and steel membrane facing. Okay, so you can see he filed a patent in 1963. That is La Terre Arme. Terre Arme means nothing but reinforced earth. Okay, reinforced earth. So here there is a company. So actually, this reinforced earth, this reinforced earth term is actually trademark. Trademark. So generally, when we call these structures as reinforced soil walls and not reinforced earth walls, because reinforced earth term is a trademark terminology. We generally tend to use reinforced soil walls. It's a generally, but both of them mean the same thing. But generally, we tend to use reinforced soil wall. Okay. So there's a company also called Reinforced Art, Arme. It's very big, huge company. So they actually deal with this. They are one of the. There are many hundreds and thousands of geotechnical companies. So they are one of the largest companies. Arme. So they have their branches all over the world. They have a very big office in India, and the largest or the tallest reinforced reinforced earth wall or reinforced soil wall is actually there in India. The tallest reinforced soil wall that is there in Tindharia in the Sikkim West Bengal border. It is there. We will see the case study after some time. After a few study phases, I will open the website and open that PDF. You can see that photo also. So the tallest reinforced earth wall that is there in India, that is constructed by the company Terre Arme. Okay, so we will see that. So there, as I said, we can use different types of reinforcement. We can use different types of reinforcement. We can have geosynthetic reinforcement. Also, we can have steel reinforcement. For geosynthetic reinforcement, we can use geotextile, geogrids, polymeric strips, grid made of strips, anything can use. And then we can have steel strips, we have steel, welded steel meshes, steel strips with anchors, twisted steel wire. You can use many options are available to us. Okay, so it based upon the location where we are using, and it depends on the designer, engineer, the cost, everything. It depends upon everything. What reinforcement you ultimately decide to choose or decide to use. Okay, so that depends upon the engineer and all the circumstances such as economy, the environment in which you are placing it. So seal strips, obviously, there are chances that you will get rusted and all those stuff. So that you have to ensure. So all those things you have to consider. So these are some of the configurations of reinforced soil walls. Okay, so you can have full light wall, you can have a stepped wall, you can have trapezoidal walls with very strong soils, you can have stepped walled in weak soil, and you can have part height walled, you can have back to back embedded walls, and you can have back to back walls, and also some other different wall configurations are shown, tired walls, okay, two tier walls. So instead of constructing a one tall wall, what we do, we construct the wall in tiers. Okay, so two tier wall is shown, then we can have a bridge over two walls. Also here four tier wall is shown. So in Sikkim, this Pakyong airport, I think they have a tiered wall there. Okay. This video is very important. This video is I have taken from Strata. Strata is also one of the big geotechnical companies out there. They manufacture geosynthetic materials and all those things, also design fake stuff. And so from there, I've taken this video. So please see this video very carefully. So in this video, you will see all the steps. Okay, all the steps of the uh, construction of a reinforcement. First you see, then I will tell you something.
Strata. With eyes on innovations, we have developed a patented systems
So
for
these are the facing blocks, facing blocks.
panel walls. Strata Wall EC is a concrete panel-faced reinforced soil wall system. The granular backfill is reinforced with strata strip geogrids to create an internally stabilized mass of reinforced concrete panel.
So here,
Strata wall system. The granular backfill is reinforced with strata strip geogrids to create.
so here they're using strip geogrid. So these strips are also like geogrid. Okay. Instead of using full geogrid, like complete geogrid fabric, they're using these strips of geogrid. Okay, so these also can. So many things are, many configurations are possible. So yeah.
Internally stabilized mass of reinforced soil. Strata strip is positively connected to the panel. Bypassing it through Strata Connect, embedded connectors which create a cavity in the concrete panel. Strata wall embedded connectors consists of strata strip geogrids, which are made from high tenacity polyester yarn and are coated with a proprietary saturation material. Strata Connect are connectors that creates C-shaped cavities within the concrete panels. Strata Connect is designed to allow easy access for the strata strip reinforcement. And precast concrete panels. Strata EC wall systems adhere to highest design safety standards. It is economical and is approved by IIT Madras, backed by Strata's assurance on quality.
Okay, I want to say that yeah, in no way I am like promoting this company. Just they've made a very good video about the whole process of reinforced soil walls. So that's why wanted to show you this. Okay, but in no way I am promoting this, so you cannot think that way. So just for saying, just so that the video is very good actually. They made this video very properly. That's why I'm just showing this video. Okay, so let us continue.
The Strata Connect inserts must be placed in position within the assembled cage and tied to the vertical bars with binding wire. The surface of panel mold has to be perfectly leveled. Correct positioning and fixing of connector on the reinforcement must be rechecked. The reinforcement cage with the connectors will be held in position using channels and S-hooks. Concrete is placed in the mold with proper vibration. Necessary precautions must be taken to ensure connectors are in place and properly protected. Tapes protecting the cavities of the SC connectors shall be removed 6 hours after casting. The cavity of all the connectors should be checked for any blockages. Lifting straps are placed through the SC connector cavity and are lifted with an overhead crane or a low-capacity tire-mounted mobile crane and carried to the area designated for curing. The panels are then covered and sprayed regularly with water or through steam curing. Excavation of the ground should be done up to the foundation level as indicated in the drawing.
Now from here it is very important for you to see. So please see from here very carefully. Okay, see the steps very carefully.
The foamwork for the leveling pad shall be fixed and concrete shall be placed within the foamwork.
So this is the leveling pad. This is the leveling pad that they have constructed.
The vertical direction and longitudinal alignments shall be continuously checked. Wooden wedges are used to align the panels in position and ensure that they maintain the correct line and batter. Wooden clamps are used for holding the panels in an upright position.
So here you can, so here is one more thing. See, you are they are placing non-woven geotextile between the gaps so that it acts as a filter. Okay, so it won't allow the soil to pass through the gaps and then come out. Loss there won't be loss of soil, but it will allow water to come out of that gaps. Okay, so we are using non-woven geotextile as filter. Huh?
Watering and compaction is carried out till the soil reaches required density, while a vibratory compactor shall be used to compact the soil matrix.
So always remember that the rolling is done. The road roller is moved in this direction. Okay, it is not all moved towards the facing of the wall because it will if you move the roller in the other direction, the direction that is not shown here, the direction perpendicular to the direction that is shown in the video, the facing blocks will fall apart. So you always have to do in this parallel direction, the rolling or the compaction.
Only hand tamping with a light mechanical tamper shall be done within 1 meter of the panel. Strutter strip reinforcement strips are inserted in the panel. The strips shall be carefully rolled and placed near the respective panels. The strips placed during the process must be in perfectly taut condition. Plinth protection to be added outside the wall to protect against cover, rodents, etc. Approved geocomposite should be placed next to the panel fascia above ground level as per the drawing.
Now this geocomposite that we saw, that is also very important, right? So what is the function? Function is both filtration and draining. So initially geocomposite means what? In between we have geonet, that is sandwiched between two geotextiles. Okay, geonet sandwiched between two geotextiles. So this geocomposite, what will it do? It will allow water to pass, but it will prevent the soil to pass. So it will allow the water to pass, then water will enter and will drain along the plane. In plane flow of water will be there and will drain out. Okay, so that's why this also is also very important.
Coping beam connecting all the top panels shall be casted. Strata wall EC is an extremely safe connection with zero failure, with no exposed steel, and hence there is no fear of corrosion and damage, further making it a cost-effective solution backed by the quality assurance of Strata.
Okay, so I hope that this was clear to you, huh? You understood everything, right? So yeah, so this was all about. So first we have the leveling pad, then we put the initial first layer of facing block, and then we slowly we construct the one. Okay, so this was all. Now we have some time left, right? Yeah, so we have around 10 minutes left, so we'll see the case study. So Tindaria, this name has changed now to GeoQuest India. In India, the name has changed. The name has changed. Previously, it was known as Terian May. Now the name has changed to GeoQuest. So this is the thing. So GeoQuest India builds world largest reinforced earth structure. So it's a reinforced earth. You are seeing that our registered trademark sign is there. So that's why I said this before. So this reinforced earth term is actually a registered trademark of this company. Okay, that's why we cannot use, generally we do not tend to use that. We tend to use the term reinforced soil structure. Okay, so I'll just download it. So this is the height of the structure is 102.8. So world tallest reinforced soil structure. All right. So the background was that in September, the Tindari, a picturesque town located in the historic Siliguri Darjeeling Hillcut Road in West Bengal, India, experienced massive landslide following an earthquake of 6.9 magnitude and heavy rainfall. The landslide significantly affected three locations, and this road was also actually this UNESCO World Heritage, the Darjeeling Himalayan Railway toy train that we say that also passes through that beside that road. Okay, it passes through the area. So due to the landslide, that railway was also disturbed, and the whole this is the main highway that joins Sikkim. Okay, that part Darjeeling to Siliguri, Darjeeling to the whole of the West Bengal and the part of the India. So that's why this was very important. So this project was very important. So you can see the project name was rehabilitation of landslide location with slope protection and drainage improvement in Dharia on NH10, 110, previous NH55 came this to this, and this to this in Darjeeling district of West Bengal. So they have a proprietary thing called TerraLink. So they use TerraLink, a composite hybrid structure, using soil nailing, anchors, facing panels, and all those things they used. The project was by the Ministry of Road Transport and Highways, Ministry of Government of India, and also the PWD Roads Department of Department Government of West Bengal. Okay, these are all the other. So these are the reinforced structures statement. So these, whatever they use, these they called as Terra link. Okay, this arrangement they called as Terra link. Okay, you can see some links like nets there and some small nailing that has been done on the structure. Okay, you can see here the slope stabilization being done. Okay, so this is how it looked while construction, and this is almost when the construction was being done. Okay. So this is the final completed project. You can see beautiful it looks, completely reinforced art structure. So the main features were stabilization of say field slope. The design of structure was done in such a way that it stabilizes the collapse slope using terrain and a bracing anchor, and also fulfills the requirement of road widening. Okay, so the road also was widened for this portion. A seismic design was also done because this is a tall structure in high seismic zone 4, as per our Indian standard. So it was done. Seismic forces were also considered. Okay, compressible panels, improvement of subsurface drainage was done, pipes were laid. Okay, these are other specifications that are given. Yeah, and design life is 100 years. So maximum height of the structure is 102.8. Live load was taken 24 kPa. Seismic coefficient was 0.24. Zone 4 as per AS 1893 part 1002. I don't know why they did I wrote 2002, because 2016 is the updated code, I think. No, God knows why they wrote this. Okay, so this was the project. See if I can get some videos also. Put up some videos. Yeah, this shooting. This is the same project, huh? You can see how vast, how tall the structure is, how vast. This is how it was made, huh? Right. So a very big project. You can see how we can make differences in the lives of the people as geotechnical engineers, right? So ultimately, if you want better connectivity, okay, you have to depend upon engineers, civil engineers, right? Without civil engineers, it's very difficult to connect region, connect remote areas, connect difficult terrain, and all those stuff. All right. So yeah. So this was all for today's class lecture. We have covered the main concept of the uh, reinforced soil walls. And what we are going to do is that uh, in tomorrow's class, we will solve a design problem of designing with reinforced soil. So during the design, while we design, we will understand, because so we can do it in two ways. Either I can first show you the steps properly, and then we can start solving the problems, or what we can do, we can directly get on with the problem. So we'll see what we do, the more easier way we will follow, so that it's easier for you to understand everything. Right. So this was all for today. So if you have any doubt, please feel free to reach out to me. Please feel free to uh, mail me or message me in WhatsApp or email me. Uh, and as usual, this video will also be uploaded, and the link will be shared in the link of the sheet that I had provided to you. So there you will get the links of this uploaded lecture, and also the this presentation also you get there. So if you have any doubt, please feel free to reach out to me anytime. I will be more than happy to help you out. And as you know, if you know some of your friends who would like to learn this course and get to learn something about geosynthetic, please let them know also. As it is a free course, everyone is more than welcome to join anytime, and it's a very concise course, right? So just in 1 week, we are just going to get it over. So today, two classes are already over. We have five more classes to go. So Wednesday, Thursday, Friday, Saturday, Sunday, five more classes, and that's all. I will try to summarize I'll try to cover up as much as I can, but I cannot go too much. Cannot cover too much because it is a very short course. So I will try to cover the important topics. All right. So thank you so much for attending today's session and have a good evening ahead. And I hope to see you again in tomorrow's session. All right. Thank you and have a great evening. Thank you.